The quantum phenomena topic test for year 12. So this deals with essentially three areas. We've got the photoelectric effect, we've got the energy levels inside atoms and spectra, and we've got the wave-particle duality. So those are the three areas that they can ask questions on. And it's really important that we don't mix up these areas, that we don't try and answer a question looking at the photoelectric effect when we're really talking about, for example, ionization. Okay, so question 1 says, experiments based on the photoelectric effect. So we know this question is the photoelectric effect topic. And it says, experiments support the particle nature of light. In such experiments, light is directed at a metal surface. State what is meant by the threshold frequency of the incident light. So the threshold frequency, the reason why we know that light cannot be a wave, why the photoelectric effect disproves the idea that light is a wave, is because of this threshold of frequency. That means that below a certain frequency, light, no matter how intense we make the light, we do not get electrons emitted. The electrons never manage to get enough energy to leave the surface of the metal. However, once we go above that threshold frequency, even low intensity light above that frequency can cause electrons to be emitted. So, what is the threshold frequency? Key word here is minimum frequency for electrons to be emitted from metal by the photoelectric effect. And you'll see when you look in the mark scheme that there are alternative answers, but essentially the key thing is that this is the minimum frequency. And note the importance of this word minimum, because there isn't just a single frequency where this happens. Any frequency above the threshold frequency, we get photoelectrons emitted. Now, explain why it's not observed below the threshold frequency. This is not, we're not asking us to restate what the threshold frequency is here. They want us to explain it. And there are two parts to this. First of all, the first part of this answer, because remember it's a 2-mark question, is that the energy of a photon depends on its frequency higher frequency photons have more energy. So that's the first part, saying that the reason why we have a threshold frequency is because the energy in a photon depends on that frequency. And so now we can say the second part, below the threshold frequency, the photon does not have enough energy to liberate or to release an electron. Okay, so the 2 marks, one for saying how the energy depends on the frequency, and the second then for saying below that frequency it doesn't have enough energy. Okay. So the next part of the question, in fact, the following parts of the question are all calculations. So this part, you must make sure that you almost always get these parts right. We have got our data and formula sheets, so we should be able to use that. So what am I told? The first thing I'm going to do is write out the numbers I'm told. I'm told that the wavelength is 5.40 by 10 to the minus 7 meters. Note they've written 5.40. So I immediately note here I've got 3 significant figures. Okay, and it's incident on a metal surface. It's a photoelectric effect which has a work function of, and they tell us that the work function is that value. So the work function is 1.40 by 10 to the minus 19 joules. The energies we're dealing with are almost always in electron volts, so that is by 10 to the minus 19 joules. Okay, and we need to calculate the energy of a single photon. So take my formula sheets, I'm going to turn to the bit on photons, and we see that we have an equation here that says the energy of the photon equals hf or equals hc over the wavelength. So energy is equal to hc over the wavelength. Therefore, the energy is equal to h and c. Come from my data sheet again, and I want you to notice how I'm writing this out. Note how I've written out all the units. It allows me to quickly check that I've done the right thing, because these seconds will cancel with these seconds to the minus 1, these meters will cancel with these meters, but you can't see the meters because it's divided by. That leaves me with joules, which are the units of energy, so I'm fairly confident I'm doing the right thing here. So on my calculator, that gives me an answer of 3.68 and then 3 recurring times 10 to the minus 19, but remember, I've got 3 significant figures, so I'm going to write the answer to 3 significant figures. 3.68 multiplied by 10 to the minus 19 joules. Then the next part, it says calculate the maximum kinetic energy of an electron. That's going to happen when the electron had a one-to-one interaction with the photon and was at the surface. And the equation again is given in our data constant sheet. So we've got HF equals the work function plus K max. Now HF is just simply the energy of the photon, so we've got that. So HF is equal to 3.68 by 10 to the minus 19 joules. The work function is equal to 1.40 by 10 to the minus 19 joules. So I can substitute these into my equation. So I've got EK max is equal to the energy of the photon, take away the work function, so that's equal to 3.68 minus 1.40 multiplied by 10 to the minus 19 joules to give me an answer of 2.28 by 10 to the minus 19 joules. Just being careful to form my numbers correctly. Okay, now part 3 in these calculations. Calculate the maximum speed. So previously we had the energy of the photon, the kinetic energy, now we want speed. So at each stage we started with these 2 pieces of information. We worked out this piece of information, the energy of the photon, then we worked out the kinetic energy of the electron. So we've got now 4 pieces of information. We have to ask ourselves, which of these pieces of information will allow us to calculate the maximum speed? Well, clearly that's going to be the kinetic energy. It's the only one that has a formula related to the speed. So we've got EK max is equal to 2.28 by 10 to the minus 19 joules from the previous part. We know that kinetic energy is equal to half mv squared, and I can rearrange this. Now we need to be careful with the rearrangement. So I'm going to do the first part of the rearrangement in a completely separate step. What I need to do is I need the V by itself. So I need to move these things away. And then when we rearrange the equation, whatever we do on one side, we have to do on the other side. So here I'm multiplying V squared by a half. So to get rid of the half, I need to divide both sides by a half. Another way I can get rid of this, because it's multiplying by half, another way I can get rid of this half is multiplying both sides by 2. So that will give me, multiplying both sides by 2, 2 times the kinetic energy is equal to mv squared. So that gives me V is equal to the square root of 2ek divided by m. And now I can just substitute in my numbers. The square root of 2 multiplied by 2.28 by 10 to the minus 19 joules, and that's divided by mass. Well, the mass of what? The mass of the electron, which we can find from here. The mass of the electron is here, 9.11 by 10 to the minus 31. So the mass is equal to 9.11 by 10 to the minus 31 kilograms. And I put that into my calculator. Which gives me an answer of 707,494 meters per second. But remember, I'm going to round this, so I could round it to 7.07 by 10 to the 5 meters per second. Like so. Okay, and I keep it in standard form. I know this answer is reasonable. If I got an answer that was bigger than 3 by 10 to the power of 8, then I know I've definitely gone wrong somewhere. Right, and then we have the last stage, which is to calculate the de Broglie wavelengths. Back into my data and formula sheet, I've got the de Broglie wavelength. It's given by this formula. So the de Broglie wavelength is equal to h divided by mv. We already have, we know what the value for h is from the data sheet, and for m. V we calculated in the previous step, so we've got that is equal to 6.63 by 10 to the minus 34 joule seconds divided by 9.11 by 10 to the minus 31 kilograms multiplied by 7.07 by 10 to the 5 meters per second. And we put all of that in and we get an answer of 1.03 by 10 to the minus 9 meters. Okay. One thing that's useful, an exercise to do is with these questions is to try, and you know that the units here are going to be meters per second, but in my equation I've got square root of joules over kilograms. It'd be useful just to show that that is the same as meters per second. It's useful practice in terms of dealing with units. Right, second question is energy levels. So this is the second topic in quantum phenomena. We're talking about energy levels. So this is not the photoelectric effect. And it tells us that we've got this hydrogen atom. It emits photons of different frequencies from these three transitions, and the three transitions result in photons being emitted in these three regions of the electromagnetic spectrum. So UV is high frequency, therefore high energy. And we've got visible, and we've got infrared. The infrared is low frequency, which gives me low energy, and this is sort of the medium frequency, so medium energy. So those are the orders, and these diagrams, the distance between the shells typically shows the difference between the energy levels. It says here it's drawn not to scale, but we do see the numbers written at the side. But generally speaking, this has got a small distance between the shells, so the amount of energy is small. This has got a moderate level of energy. This has got a high level of energy, which tells us which ones these should be. So A, small energy change, so it's low frequency, so it's infrared. The B is moderate, and the C is ultraviolet, with a high level of energy. Okay. Now we've got two ways to excite a hydrogen atom: by collision with a free electron or by absorption of a photon. Explain why for a particular transition the photon must have an exact amount of energy, whereas the free electron only needs a minimum amount of kinetic energy. So there are two things here. There are two ideas to deal with here. So we need to answer for both of them. Okay. Now in both cases, we're talking about the excitation of a hydrogen atom. So this is because there is the photon, or the collision with the free electron, provide the energy for the electron to move to higher levels in the hydrogen atom. So I'm going to write that down first. So this is the absorption of a photon, or the collision with free electron provides the energy needed for, and I'm going to call this an orbital electron to move to a higher energy level. Okay, now I'm going to change my color pen for the, I'm going to talk about the photon bit first of all. Okay, just before that, I'm going to add one further sentence just to make sure that we're ready for what we're saying. This requires an exact amount of energy. Now, here we go for the photon. The photon has a one-to-one interaction with the electron, so all its energy is absorbed. Therefore, it must have the exact amount needed. That's for the photon. Then for the free electron can transfer part of its kinetic energy to, well, S, and continue with lower kinetic energy. Okay, so the free electron, it doesn't need an exact amount because it can just transfer the amount needed, and then if there's anything left over, it can just continue, whereas the photon has to transfer all of its energy, so it must have exactly the same amount. Right, next question says that we're told that it's a sample of cesium exposed to these three photons, and we're told the threshold frequency has this value. Determine whether any of these transitions would produce photons to cause the electrons to be emitted. Now, there's two ways we can do this. We can either do it by method one, is determine the work function from the threshold frequency, or the other option is determine the frequencies of the photons. Either of those approaches is fine. I'm going to choose to look at the energies, but using the frequencies is fine. So if we look at, first of all, the energies of the photons. So we have for the UV, we had visible light, and we had infrared. The UV, it went from 13.6 to 3.4. So it has 10.2 electron volts of energy. The visible, it went from 3.4, 1.5. It has 1.9 electron volts of energy, and the infrared went from 1.5 to 0.85. So it has 0.65 electron volts. So those are the energies of the photon. Now let's take a look at the work function. So the threshold frequency at the threshold frequency, the kinetic energy of the photoemitted electrons is 0. So the maximum kinetic energy is 0, which means that HF is equal to the work function. So what have we got? We've got H, therefore the work function is equal to 6.63 by 10 to the minus 34 seconds multiplied by 5.1 by 10 to the 14 hertz. Again, just prove to yourself those units work correctly. So we've got 6.63 to the minus 34 multiplied by 5.1 to 14 that equals 3.38 by 10 to the minus 19 joules. And to convert that into electron volts, that equals 3.38 10 to the minus 19 divided by 1.6 by 10 to the minus 19. That's joules per electron volt, which gives me 3.38 19 divided by 1.6 19, which is equal to 2.11 electron volts. So looking at this is below the threshold, this is below the work function, this is below the work function, so this one. Therefore, transition C that's a question, how did they put it? Yes, could cause electrons to be emitted as the energy of the photon is greater than the work function. Okay, so this last sentence, it's really important to include this. The question asks, determine whether any of the transitions could produce photons, etc., etc. So as well as doing the calculations, you need to have a sentence that gives your answer to the question. Okay, so that's important. Okay, now the last part, we have the photons each have energy 12.1 electron volts, which are incident on the surface of the cesium sample. Calculate the maximum speed of the electrons emitted from the cesium. So what information do we have? Well, we have what the energy of the photon is. We know what the threshold frequency of the cesium, and in fact we've worked out what the work function is, and we're interested in the maximum speed of the electrons. So if we think about it, when the information we've got, the energy of the photon, the work function, that means that we can use this equation from our data sheet. So we've got HF, the energy of the photon, is equal to the work function plus EK max, because the electrons with maximum speed have got maximum kinetic energy. So HF is equal to 12.1 electron volts. The work function we worked out was 2.11 electron volts, and we're trying to get the maximum kinetic energy. So the maximum kinetic energy is equal to HF minus the work function. So that is 12.1, take away 2.11 is 9.99 electron volts. Okay, now I need to convert this to joules. So that's going to be 9.99 electron volts multiplied by 1.6 by 10 to the minus 19 joules per electron volt. So that's equal to 1.60 by 10 to the minus 18 joules. Now notice, by the way, I was typing everything on my calculator there, even though these sort of things I could do in my head. There's no reason to do things in your head in physics, and you'd want to try and avoid making unnecessary arithmetic errors. So don't be afraid to use your calculator. You'd never have to do any mental arithmetic in physics. Okay, so we've got the kinetic energy. We're now going to use our usual equation for kinetic energy and rearrange that. Gives me that the maximum speed is going to be the square root of the 2 times the maximum kinetic energy divided by the mass of the electron. So that gives me Vmax is equal to the square root of 2 times 1.60 by 10 to the minus 18 joules divided by 9.11 by 10 to the minus 31 kilograms. Again, you can prove to yourself that the units work out correctly. Root of the answer, and that gives me an answer of this, which is, I've got 1, 2, 3, 4, 5, 6. So I've got 1.6 And I could write this as 7 by 10 to the 6 meters per second. You'd also could have written 1.9, but here I'm staying with 3 significant figures, as that's what I've been given.